today. Must be the recording starting. So yeah, student seminar today. We'll be presenting, so you'll be there. But others, hope you can attend. There'll be some introductions and some refreshments at the end. Might be kind of a long day because there's lots of presenting, so it'll be interesting for the diversity of things there. Today we'll talk about robustness in chapter 3, and on Monday go into kind of chapter 3 and 4 are a similar topic in the sense that they're looking at alternatives to T procedures and things like unequal variances, skewness, and so on. And so we'll look at that aspect of it. And Wednesday we'll do more of that, but also parts of transformations, and the second homework is due then. Right? And so I thought about things, I said that students do a presentation on a topic, right? And how can that be kind of more normalized and integrated into things so it feels like something you have time to do and it fits within the course. And so I decided to write up a page here called Student Topic 1, these graphs of data, skewness, outliers, patterns, right? And so I will put these along with a homework assignment, right? And so all students can look at them. There's nothing for everybody to turn in, but one student would make a short presentation on the day that the homework is due. Now, one of the problems on the homework has a transformation in it, so it kind of builds off that. But it would be interesting to look at some broader data structures and so on, right? To see some other examples of transformations. How big of an impact does a transformation do? Just to kind of get a sense of that. So the idea of this, so one student would do this. It doesn't have to be a overly long presentation. So in R, there's several different data sets that are available. Just by typing data and then 2 parentheses brings up a list of data sets that are there that are part of the default issue of R, and you don't have to do anything else besides that to access them. Some interesting ones, I think, in terms of shape. There's rivers. There's ones about stopping distance of cars. There's something about Old Faithful eruptions. Some other environmental ones. And then things on human populations. There's a data set called Swiss, another one called state.x77. So those are a few data sets there. And the idea of the presentation would be to say something about, pick a few of those, 3 to 4, maybe 3, to talk about briefly, and show a graph of what the data set is. It could be histogram, box plot, or maybe both, right? Something like that. And then what happens when you transform the data? What happens when you take the square root? What happens when you take a ratio of variables, maybe? You can do different things. If there's one big outlier, if you can delete that outlier and see what happens to the graph, does that kind of appreciably change the shape? So the presentation for, say, 3 data sets would be, say, describe briefly what this variable is, right? Show a graph one way and show a graph the other way, right? If you wanted to look at confidence intervals before and after transformation, you could show that, but just kind of showing the graphs to see that the pictures, I think it's informative to see the variety of things that you could have. Not everything is skew in these examples. You could pick other examples, right? But that would be the idea of it, right? So the student presenting doesn't necessarily need to make a handout. You could put the graphs you make into a PowerPoint, so it's easy to kind of go through about, if it's 3 data sets, a couple pictures each, maybe 6 slides or something to go through with a little. You can write out more details if that aids you in making a presentation. Alternatively, you could just put together an R script where there's some commands, right? And you could load it up and you could kind of click through it. If you make a PowerPoint or any other type of document or an R script file, we can make that available online, and you don't necessarily have to pay for copying, things like that. Students can follow along and try it on their own, right? So, but that would be the idea. So, not every homework assignment, but many of them, right? And so, a consequence of this is everybody will do this once, right, rather than, twice. So that kind of fits in better. But my thinking with that as well is, even if though it's not assigned, it's something that most of you will be able to kind of try out, look at it, for yourselves, even if you're not presenting. So there's kind of a little more self-study to gain the knowledge and experience of doing these things, even if it's not formally graded that way. So that would be due Wednesday, right? And so either we could go on volunteers, and everybody would have to do this once, or I can assign people, right? So there's Hattie's technically auditing, so she doesn't have to make presentations. She has credit for this from a student experience earlier. So there's 8 of you that would do the presentations. Do you want me to assign you an order, a sequence? Is that just easier than taking volunteers so that you know that you can do it? Right. So I'll go ahead and, without much response, I'll go ahead and do that. So to do that, right, I use R, right? So if you set random number seed for today's day, right, the 6th, right, and then you sample the numbers 1 through 8, because it's 8 students taking it for a grade, and replace equals false, right? And pick the numbers, you get 5 numbers. So if I take alphabetically in order, the 5th person alphabetically by last name would get to do the first one, right? And so that actually is Connor, is the 5th one, alphabetically by last name. So the order for these, and they won't be every homework, because there's this one time that the midterm project is due, so let's not do a presentation that day. And then there's a little bit of flexibility at the end, because it won't be that crowded. So the order for these things would be Connor would be first, and then Lily the second, and then Annie, then Yifei, and then Zhen Jiang, right? Then Courtney, right? Then Dan, and finally Maura gets to do the last one, right? And so this would be the 9. So if it's next Wednesday, that's 11, 19, 1, so you get to do the first presentation. By having them do with the homework on Wednesdays, then eventually the homeworks will move to Fridays once we have that extra day of break in the schedule. But there'll be a couple office hours. So talking on Monday and Tuesday would be a time to just kind of talk about that. And again, it's not an overly long presentation, but it's a way for you to present something in class, do a little more presentation, and do a little bit more exploration, right? And communicate a lot. It's not fully flipping the classroom, but it's allowing you to do a little more presentation. Right? So, but any questions about that? I hope by kind of formally incorporating it with the homeworks and assignment that it's clearer and that it's well structured and that everybody's kind of following along as well. So, okay. So Connor, if you want to meet with me Monday or Tuesday to talk about that. This also will put it, thinking about it a little bit further out, so it's not like next class period, but it's like, in a week you want to do this, so it's a little bit more manageable to scheduling. So. All right. And if it happens that something is just terrible with the schedule or something, or some topic comes up and you really love it, maybe, we could talk about switching as long as everybody does it, but unless there's any other reason, we'll just try to keep it like that. Okay. So today's topic, right, is we've been doing these testing procedures or confidence intervals, right? And the idea of these is there are some assumptions underlying these, right? And so this idea of robustness, there's an area of statistical research, statistical methods research called robust statistics. It was very big in the 60s and 1960s, 1970s with alternatives to doing standardized procedures that were used at the time. Often they're computer-based, so they really took off after that time, right? So the kind of preface for this, right, is that our methods that we're using are built on assumptions. And the assumptions that we have really concern data collection. On one hand, they concern data collection. And they can also concern the distributions of data. All things really about, many things about the shape of the distribution. Is it symmetric? Does it have a long tail? Does it have heavy tails? Does it have outliers? Does it have multiple nodes? And things like that. And the goal of the procedures is to generalize from data, from a data sample to a population. And this process of generalizing from data to a population, you have a method. If it's built on assumptions, and some of the assumptions aren't really very valid, then the inference might not be that useful, might be inaccurate, right? So, so the method the methods can give an inaccurate generalization. Right? If assumptions are wrong. And in these things, that the type of assumptions generally that are useful for generalization could be something about the data collection, like if it's not a random sample or if it's a biased sample, like a self-selection. So the data collection might not produce something that's representative and useful, and so there would be a difference. Or if the methods are built on something like symmetry or equivariances, and that's kind of built into the assumptions of how things are derived and set up, things can go a little haywire, right? But methods can be very accurate. Methods can give precise inferences. So standard errors for estimates can be small, but not be accurate. So you can have bias that's present in there. So even if a method gives you small standard errors and gives you a very precise inference, it doesn't mean that it's really, working well. That there could be issues, like the population is systematically different, and so it won't be enough just to compare methods by the standard error, which method may give you a smaller, more precise estimate. There's a few classic examples of this. Back in elections in the 1930s, the election, that involved Dewey versus Truman, right? There was a Reader's poll, Reader's Digest sample. Right, and this is more than 1 million people. Right, where they sampled the Reader's Digest magazine, one of the big magazines back at that time, right? Sampled 1 million of its readers, and they said that Dewey was who they're going to vote for president. But the people that were getting the Reader's Digest magazine weren't very representative of all the voters. Magazines were expensive, incomes were much less, the reading population, literacy just was not as high, and back then, and so the people that were reading the paying to subscribe and reading it, and willing to participate in a poll about that were not like the general voters, and Truman won, handily, right? And so it was really off because there was a bias there. Right? So this one was not a random sample. Right, and so there was a bias there. Other big studies of the polio vaccine, the Salk polio vaccine in the 1950s. One study was a National Foundation for Infant Paralysis, right? And they had more than 100,000, almost 1 million children in the study, right? But it wasn't fully a randomized study. They took grade 2 as a control versus grades 1 and 3. And so there was a confounding bias. Right, due to consent. Right, they had one group that received the vaccine. They had to consent, right, and then they could refuse. The people they used as controls didn't have to consent. They were just the hospital records or the records of the rates of disease of that other population. So when they're comparing two groups, one of them had a little bit more, this one selection factor versus the other. And even though they had hundreds of thousands of children involved in this study, it wasn't convincing. A different randomized study was done that showed a bigger result and avoided that. And so polio vaccines were adopted. But you can have very, very large studies. You can have other methods that produce very, very small standard errors, and it just won't necessarily be that good. In the modern era, our era, there's a number of companies that have set up very large internet panels, right? Doing 1 million plus people. Gallup organization, others have set up knowledge networks, and a few other companies have set up these internet panels where they get people to volunteer to participate. Right? They invite them to be part of their panel. They're sending out things through social media, all their other contacts and operations, and people participate. When people participate, they provide the internet companies with tons and tons of information. Age, demographics, income, education, health, history, and all that, right? And they get up couple million people signing up. And then when they want to do a survey, they already have people with their internet access and their emails and maybe their phone numbers and so on, so they can send out a message to this panel, and presumably people will then answer right away. So instead of the expense of a telephone survey or something, or trying to recruit samples, they've already kind of gone through one part of that step. And then they can use these people over and over again for different things. Well, it's very large, but there's some obviously selection issues here. Right? Oh, and they pay the people a little bit, right, for their participation. But it's still cheaper than trying to recruit brand new people. But these people, right, they had to volunteer, they have to use the internet, they have to be interested in this, possibly maybe an economic difference, certainly there's an education difference. And then there's, at that final step, even if they send it to 1 million people, they still might only get a couple hundred to respond. When people don't, even if they say they're going to participate, the pay isn't so much that they're making a living doing this. And it's like, if you, in the next 2 days, you can answer this, you're in it. And so there's still a selection bias. And so a big area of research is, can you use the demographics and everything you know about these people to adjust from the respondents to a more general population? And so statistical methods, if you did this enough, you get a very big response, and standard procedures would give a real small standard error, but doing some type of adjustment really becomes a question, right? So that doesn't say too much really about comparing procedures. This is more about the data collection and randoms. But the idea that you can get inferences that don't quite hit the target is part of it, right? So our tests and confidence intervals are procedures. You can think of them as procedures, right? What do you do with data? Once you have your data, what do you do with it? How do you make a statement? You report averages, means. How do you make a confidence interval? How do you make a decision, right? And so once you get data, it tells you what to do. And so in hypothesis tests, right, we have a significance level, level given by alpha, like 0.05, something like that. And so we're going to reject a null hypothesis if the p-value, if the p-value we calculate from our null distribution or randomization distribution is less than or equal to alpha. Well, what does that significance level really signify? What does it really mean, right? So if the null hypothesis is really true, then we're rejecting if we're out in that 0.05 tails, if we're extreme, more rare than 5%. Right? So if the null hypothesis is true, right, we want our procedure to reject. That's not clear. We want our procedure to reject H0 no more than the 100 times alpha percent of the time. Right? So we want our rejection to be no more than 5% if the null hypothesis is really true. And if it's rejecting it more often, that's not really calibrated to our procedure. Right? So if it's, I'll just write a word here, calibration. Right? Calibration in the statistical sense is like just how you would calibrate a machine or an operation. Right? You want it to perform within a certain level of tolerance almost all the time and not make an error more so than you would specify. And so if our error, our probability of a type 1 error of rejecting when the null hypothesis is true is alpha, we want our procedure to be calibrated so in the long run it actually gives us about 5% errors, or maybe less. Right? We could be satisfied if it's less, but not if it's more. Because if we're making more errors than we would hope. Right? For a confidence interval, right, you have a similar corresponding thing, confidence interval or CI. Right? Confidence level, 100 times 1 minus alpha percent. So if alpha is 0.05, this would be a 95% confidence interval. Write the notes, right? Well, we're aiming for the population value, right? And so we would like the intervals to match up to that and cover it, right? And so for calling something a 95% confidence interval, we want to be at least 95% confident, at least 95%, or in general 100, 1 minus alpha percent of intervals should cover the population target parameters. Now if our intervals cover more, 96, 97, 98, that's good. That's fine. Generally we want intervals to be small, so that would be another thing. We do want precise inference, but we don't want to make overly narrow intervals that miss, right? So we want at least 95% of the interval should cover. And the original definition back in the 1930s and so on about what is a hypothesis test, what does a confidence interval mean, it was phrased this way, that at least 95% coverage. And then you can debate methods. If you have two methods that get at least 95% and one is more precise, then that can be preferred. But we want to make sure that that happens. So something is robust to an assumption, right? If that assumption isn't quite met, or if assumption fails to some degree, if we still get a valid conclusion and it's still operating within our tolerances, so it's still reasonably calibrated to how we want our procedure to go, right? So robustness, then a robust procedure gives valid inferences. So valid inferences, I'll write in here this word calibrated, meaning that they achieve, in the long run, they would achieve with these type of data that depart from assumptions. A robust procedure give out even if assumptions are not true. Even if maybe some assumptions are somewhat not true. For most procedures or inference things, you can probably break it, right? You can probably get something that's so far out of what you would expect that it just doesn't operate very, very well. But if there's milder departures from it, from some of the assumptions, and if it still gives well-calibrated inference, you're still going to get pretty close to the 5% significance or 95% coverage, then it seems a little safer to use. And you can use it in a more broad things to do, right? So, okay. But any questions? So we want to look at this and see how it works with different examples. And the concern about robustness will also lead us to do alternate procedures, things that have less assumptions. Because if you have a procedure that is calibrated but doesn't have many assumptions, then it's in some sense safer to use. There's consequences that we'll look at. We want accuracy, precision. Some of the alternatives might not be quite as precise, but they might be more calibrated. So there's a debate, there's a trade-off that sometimes happen. So our two sample, independent sample, t-tests procedures. We had two groups, and we summarized them. Two groups, N1 and 1 into and the other one. We're going to take the average of the first group and the average of the second group. There's a standard deviation for the first and a standard deviation for the second, and we're going to pool these things together to get a pooled one. We're going to use a t-distribution with its degrees of freedom, n1 plus n2 minus 2, and we're going to test a hypothesis. Are the means equal versus either not equal by looking at a t-statistic. Our t-statistic is going to be the difference in the sample averages, right? And this pooled combination estimate of variance, and 1 over n1 plus 1 over n2. Right? And we're going to compare that to a t-distribution. And a confidence interval does a lot of the same things. We could pool, get our standard error, and our confidence interval would go y bar 1 minus y bar 2 plus or minus a t-value with a certain degrees of freedom, 1 minus alpha over 2. We got that upper tail, and then this standard error, SP. So what assumptions were underlying these procedures.
Normality?
Normality, right? So the original data, okay, in a strict sense, if we say that the original data measurements, N1 measurements that are normal, N2 measurements are normal. Right? So, I'll put some assumptions here so there's more time to write everything that's up there. Right? The data, so Y1I, Y2I, for the two groups, the individual measurements are normally distributed. So that, but it's by group, right? So you can have, they don't have to be the same normal, or you can have one normal for the first group and another normal for the second group, but kind of bell-shaped curves, right? And it's hard to, in a finite sample, to say it's exactly normal or not, but it has to look close enough, right? It has to be believable that it's a normal sample. Good. So that's one key assumption. Yeah?
Independent?
Yeah, there's some independence. What's independent? Yeah, there's independent measurements, right, inside of each group, right? So independent, N1 observations are independent of those others, and the N2 are independent, you could say within groups. So if there was a, that's really, also, to know something about that, you have to know something about data collection. Right? That's almost outside of the statistics and numbers. Is it correlated? Is it clustered? So really understanding how the data, were there pairs of data within the first group somehow, knowing something about that, you'd have to kind of know that outside of the numbers, right? Independent within groups, but then also the two groups are independent, right? It's not matched pairs. So independent within groups and simply independent groups. You could expand this one with normality a little bit, right? You could break it down. So it's bell-shaped, right? So you could make that bell-shaped. You could also express it as symmetric as opposed to skew, right? In there. There's one other consequence of being normally distributed, right? In terms of outliers, right? Normals don't have a lot of outliers. There's a very, pretty strong probability limit on having things that are more than 3 or 4 or 5 standard deviations away from the center. So kind of few outliers. And the outliers, even if they're there, are not massively outside of the data set. Right? Do we have to have equal sample sizes? We don't necessarily have to have equal sample sizes, right? So N1 equals N2 is not an assumption. So the procedure should work there. Right? There's one other assumption to put in that list before talking about that one. Right? In doing this, we pooled this, right? So doing one combined estimate of the standard deviation is valid if the two groups are equally spread out, right? If you had two groups where one was very narrow and the other was very, very wide, right? Or you could have a mean difference, right? And one's very narrow and the other is very, very wide. It wouldn't quite fit the model. It's a deviation in some sense, right? So maybe the procedure is sensitive to that, right? So N1, N2 is not an assumption. It should work, right? But is it desirable to have N1 equals N2? It might not be strictly an assumption, but maybe other departures or other issues are have less impact if you have basically equal sample sizes. Right? If you look at the examples in the book, and I don't think we're going to talk too much about them today, but they can come up as we go further. There's the example 0301 on cloud seeding. Here you have N1 is 26 and N2 is 26. And I believe this is two independent samples. It's not really clear to me that it wouldn't be paired, right? That the data description there is not that detailed, where I kind of wonder. But it's equal. That second example in there on Vietnam veterans and Agent Orange, there's one group that's 646 and N2 that's 97 veterans who served in Vietnam in areas where they're using Agent Orange, and the 97 veterans from that time period that we're doing it. Right? But it's pretty different, right? Is that any type of problem? It doesn't technically violate an assumption, but it could be an important thing, right? So let's do just a little bit of math. If sigma 1 equals sigma 2, right, so the variances are equal, right? And the variance of y bar 1 minus y bar 2 of our statistic is going to be sigma 1 squared over n1 plus sigma 2 squared over n2. And let's say our budget sample size is n equals n1 plus n2. So we have a certain amount of data that we can process. We can process n observations, and they have to be split in two groups. Right. Randomized experiment, you can think about going in one group versus the other, and n is the total sample size, and our choice is going to be to split that up. Right. How should we split it up to minimize this variance? Right. If these things are equal, let's just call it sigma. Right, so then this is sigma squared times 1 over n1 plus 1 over n2, and we want to minimize, right? It'd be desirable, so it's a goal, to minimize the 1 over n1 plus 1 over n2, subject to n to this constraint. Right, so how do you do a problem? What's one way to do a problem like this, right? First of all, is the goal clear, right? So we have a budget that gives us a sample size of little n, and we're going to split it into two groups. What's a good way to split it? If the variances are equal, it's the same as minimizing that function, right? Well, we have two sample sizes here, but if n is known, we really have a constraint. So N2 is, we can choose the number for the first group, and then what's left over out of our allocation is there. So it's really minimizing 1 over N1 plus 1 over, and this N2, right, choosing that given a fixed value of n. So minimizing this over the choice of N1. So to find a minimum or maximum of a function, right, is a derivative. Right? Take a derivative of these things. So you can take a derivative of this measure, 1 over n1 plus 1 over that, with respect to n1, because n1 is what we're going to choose. Right? So we're going to take the dn1 of 1 over n1 plus 1 over n minus n1. Well, 1 over n1 is like n1 to the negative 1, so there's a negative, and then n1 squared. And then this one, we have n minus n1 here. The derivative of that, there's a negative 1. But by chain rule, we also have to take a derivative in here, and here's a negative. So we get a negative because it's 1 over, and we get a negative because it's there. And that's going to be the derivatives. And we set that equal to 0. So that equation that we've gotten here, -1 over n1 squared plus 1 over n minus n1 squared equals 0. If you add this one to the other side and multiply through, you get n1 squared equals n minus n1 squared. Those two things have to be equal. If you take n1 squared equals n squared minus 2n n1 plus n1 squared. Then the n1's cancel and you get 0 equals n squared minus 2n n1. You pull out one of the n's, 0 equals n minus 2n1. And so n1 ends up being n over 2. So if the variances are equal, right, it would be desirable in terms of that variance and accuracy of the statistic, right, to split them in half. So it is desirable, right, in terms of variance, that n1 equals n2. So even if it's not an assumption of the procedure for it to work out and do valid inference, right, by if they're really equal spread, by choosing them to be equal, then it would provide smaller variance. So sometimes we could look at something like that. And so we're going to look at, to kind of go back to that, is this procedure impacted by any of these distributions? Let's look at one simulation today to kind of put it in context of looking at something. So this was not necessarily an assumption to have that n1 equals n2, but it's desirable to have it equal for efficiency standpoint. And now what we want to look at in the simulation is, if we deviate from one of the assumptions, I guess for a one sample test, we're just going to make it simpler to begin with. How do we see whether it's actually working or not? Where do we see evidence of a failure, right, of some departure? How do you know, based on a simulation, that it's not getting the coverage or the significance levels that you really want? So a chi-square distribution is a skew distribution. Right? So this, let's write down what we're doing. So now simulate non-normal data. In this case, we're just going to have one sample. It's not as complex as what we were talking about as the source of those. We're just one sample. The assumptions are very similar. Normal data, right? Independence and something like that. Right? A chi-square distribution with 4 degrees of freedom is a distribution that looks kind of like this. And if it starts at 0, it has a mean of 4. So a chi-square degrees of freedom probability distribution, where we subtract 4 from every value, is going to be centered at 0. So here's -4, here's 0. So it would come up like this. So if we take a chi-square with 4, just a random probability distribution with that shape, and subtract 4, it ends up with an average around 0. So in this case, the null hypothesis is that the average really is 0. Just a little mechanism for simulating data that have a mean 0 and skewness. So here's a histogram of the data. Here's 10,000 values from that one. So this particular one sample example, right, is averages nearly 0, but it's skewed. Right? So if we do a confidence interval or hypothesis test, well, we'll do a hypothesis test, is the average 0 or not? Well, we really generated data from a zero mean population, so the null hypothesis is true. We shouldn't reject it. We want to see how, if we did this many, many times with different sample sizes, what would happen. Right? So let's take one sample as an example. Let's say I'm going to take 20. I'm going to use something called degrees of freedom 4 that impacts the shape there. And my data, random chi-square. Right? And I'm going to subtract that degrees of freedom of 4, and that's going to make it centered at 0 on average. Right? And the mean is negative 0.83. We can do our histogram of our actual little data set here. This is our little data set for 20 observations. The average is a little bit lower. And if we run this t-test command, it just tests, is it 0 or not? So our mean was negative 0.83. Our confidence interval is there, 95% confidence interval, negative 2.11 up to 0.45. It includes 0. So we don't reject 0. The p-value is 0.19, which is bigger than 0.05. So we don't reject. So in this case, we've generated a sample, and it's consistent with 0 being the mean. We don't reject, which is good. Right? That's what we would hope would happen. That won't always happen. Every once in a while, you're going to get too much that's too low, or a few that are too big, and the mean is going to be far enough away that the confidence interval will miss, or the p-value that's implied by that will be small, less than 0.05, and we will reject. Right? So our question is, in the long run, how often do we actually reject or miss? And we can simulate that. We can also, the t-test command is actually produces a list. Names, t.test, my data set. Once that runs, it actually has all of these things hanging on to it there. It has a p-value, the null parameter value, the statistics value, a confidence interval, standard error, and other things. So that stuff is actually hanging on to that object once you do the t.test. You can save that if you wanted to do different things. And then you can pull off individual parts of it. Right? What you see here is R's default way of presenting that information. It's supposed to be readable. The p-value that it pulls off is 0.19. So that was one sample, but now let's do 10,000 samples. Set the random number seed to today's date. 10,000, sample size 20. We're going to have the 10,000 p-values that we're going to pull off. I put p20 because it's a sample size of 20. So we're going to go through this 10,000 times, generate data, do the test, pull off the p-value, and save it. So we're going to get all these p-values. We run that. I make a histogram of the p-values. What do you know about this histogram of these 10,000 p-values? It's kind of flat, right? Except for a little extra out there. How many of those p-values are less than 0.05? What's our goal? What do we hope for?
5% of them?
Yeah, we want 5%. We want to reject 5% or less if we have a 5% significance level. Right? So it is, oh, wait, run it again. It's actually about 6%. A little bit higher rate of rejection, right? Why is this happening? Right? Well, the data were skewed. 20 is not that big of a sample. So you're a little bit more likely to get some big values or small values. It's going one way or the other. We can track the confidence intervals to see if do we hit low or higher. But anyway, it's a little bit off. It's rejecting a little bit more because the sampling distribution is quite not normal, and so we get values that are further from 0 a little bit more often than it would be if the assumptions were exactly true. What happens if we take a sample size of 10? Is this deviation, this non-normality, is that going to be worse or better? Probably worse, right? Right, 'cause you average more things together, the sampling distribution gets more. So here's 10, here's save the p's. Now changing in here is going to give us 10. I'm going to save the p-values in that one. And here's that run. Oops. I think I plopped it down in the middle, and so I thought here's 10. I'll start back here. 10, that, and run it. Good. Histogram. So these histograms of these p-values is a little more accented there. Right? And it's about 7%. So it's rejecting about 7% of the time, so it's making more errors than we would typically like. So, what are the implications of this in, say, a medical study? If you're making more type 1 errors and rejecting the null hypothesis more, is you're saying things are significantly different from 0, and there really is an effect, when in reality there's not. Right? So you're saying a medicine is effective more often than you should be. Right? So it's not a good decision. Right? Or you're saying that we should invest in something, more in education, more in training, or something like that, where you think there's a benefit, but in reality there's not. And it's making that incorrect decision more often, so it's misleading you. So yeah, with 20, this was the plot. I made about 6% over, or 6% instead of 5. When it was 10, we got 7%. Probably a sample size of 5 would be even worse because the skewness would still be having more of an impact. How about at 40? So here's 40, histogram of 40. There's a little bit there. Again, it was about 6%. 20 and 40, so well, let's do 80 and see if we get anything else. Right? At 80, this particular sample, it is a sample of 10,000, so it's not the complete distribution. But that's about 5%. It's actually a little bit less. So 80 seems to kind of erase most of the impact of the non-normality. Right? So that skewness with an adequate sample size, somewhere between 40 and 80 maybe, right, seems to be less of a concern. But in small sample sizes, it's more of a concern. Right? And this was one form of skewness. Right? You can have things that are much more skewed than that chi-squared, right, in reality. So we get these messages. The more skewed the original data, the bigger sample size you really have to put strict stock and belief in what the p-value is telling you, right? In terms of interpreting it. And this is related to the central limit theorem. So I'm just going to generate averages, 10,000 averages, and I'm going to try to do it, efficiently here in terms of the code. So this is, I'm going to generate, 10,000 samples, each of size 10, so 100,000 observations from that. Subtract 4 from each, so that puts it at 0. And I'm putting in this matrix with 10,000 rows and 10 across, and this apply command then takes the averages for each row. So it's going to give me quickly 10,000 averages for that, not an alpha code. Right. And then I'm going to make some graphs. So this parameter thing, this is the graphical parameter. It's got a matrix format for the rows, so it puts one row and 2 columns, so it can get to 2 at once. This is a histogram of means based on samples of size 10, and this is a normal probability plot. So this thing will be roughly straight if the data over here are close to normal. And the fact that it bends a little bit means that it's a little bit short over here and a little bit long over here. So it's a little bit deviation from normality. This is the average, right? So we particularly, even if the data itself are not normal, we really do want the sampling distribution of the average to be normal. And so it's not quite there. If we do that with 20, there's the picture. So it's a small change, right? So it's kind of a little deviation there, and then a little deviation there, and as you keep going through these, so 40 is pulling it in a little bit more, and with 80, there's still a tiny bit of deviation, but it's pretty close to straight throughout the range. Yeah, 10,000 to see 5 or 10 points, a little bit more, a little bit less. It's not a huge huge fraction. Right? So, right. So in looking at, right, robustness, right, and the properties of statistical procedures, what we'll do in these chapters 3 and 4, in terms of some of these simulations and examples, right, is we're going to examine how deviations from assumptions impact error, right, and coverage rates. Of our inferences. And so we've seen one example that if the data aren't quite normal and you have a small sample size, you can make more errors than you intend, and that's not good. Right? That'll also motivate us to maybe look at alternative procedures that aren't as sensitive to that. We'll do more of that on Monday. So on Monday, it's part of chapter 3, part of chapter 4, because some of the methods and some of the diagnostics and looking at the impacts of deviations and then suggesting alternatives. On Monday, we'll focus more on the chapter, the 2 sample things. So 2 sample things on Monday, and then on Wednesday, we'll see a little bit more about transformations and some 1 sample things again. Any questions about the thing? So, all right, well, have a good weekend.
Oh my god. Never going I'll see you later. See you. Thank you.
Yes. Oh, this is just repeating the value 0 10,000 times. The other way that I set that up sometimes would use numeric value length that equal b, and this REP is just repeating a number. It's kind of just setting up a default place to store the p-values. So it's set up, puts 0 in there all to begin with, and then each time it goes through this, it replaces 1 with one p-value based on 1 simulation.
Oh.
So how many of those p-values are less than or equal to 0.05?
So what do we do?
Dividing by b. So this was done 10,000 times.
Yeah.
So we're dividing by 10,000, so this is going to be the fraction. So the sum here will count how many times it's less than or equal to 0.05.
Oh.
And then the dividing will give the fraction. So that's where we're getting the 7% or 6% as a rate, so it's being bigger. So.
Okay. Thank
Okay,
you so
sure.
much.